Hi, it's Bob here, and I'd like to showcase an Arduino project I've recently made. It's a binary counter. It features 4 LEDs that represent a binary number and 2 buttons for the user to move the counter up and down. I also included a 7-segment display which shows the value of the counter in hexadecimal. The code which controls the circuit is contained on the Arduino's microprocessor. To program the Arduino, it connects to VS Code using a USB cable. I'm using the Arduino VS Code extension, which provides options to select the Arduino type and port. When first working on the project, I used a breadboard and Arduino Uno to make a rough prototype. The breadboard allows components and connections to be changed quickly without having to solder them permanently. Once I knew how the circuit would be designed, I worked out a tidier layout using Figma. This allowed me to position the components and utilise the available space. Then I soldered the actual components to a perf board and added connecting wires. The Arduino Nano is attached using header pins so that it can be removed and reused, but the cheap components are soldered straight to the board. There are 3 important features of this circuit I'd like to explain in more detail. The LEDs counting in binary, the 7-segment display, and the digital switches. Suppose we want to physically represent a number in a way that we can look at it later and work out what the number was. One way we could do this is to use beakers of water that have divisions like this. If I wanted to represent the number 4, I could put 4 measures of water in the beaker. This is similar to how we could count numbers with a tally. One problem with this method, however, is that it doesn't scale well with large numbers. To represent 1 million, we would need 1 million measures of water. A way to improve this method would be weighted representation, where measures of water in different beakers represent different amounts of units. I'm going to choose the number 5 for our water beaker system, and the number of measures each beaker can hold is 1 less than this, 4. To represent 1, 2, 3, or 4, we can do as before. If I try to add a 5th measure, the beaker will overflow. So, to represent 5, I will use 1 measure in the 2nd beaker. Each measure in the 2nd beaker is worth 5 units. So, if we have 2 measures of water in the 2nd beaker, it would be worth 10 units. 3 would be 15, and so on. Again, if I try to add a 5th measure to the 2nd beaker, it would overflow. The 5th measure would make a total of 25, so we add a 3rd beaker where each measure is worth 25 units. To describe the number 33, we can have 1 measure in the 3rd beaker that's worth 25 units, 1 measure in the 2nd beaker that's worth 5 units, and 3 units in the 1st beaker. Using weighted representation, we have represented 33 units using only 5 measures of water. What we've actually described here is a base 5 number system. If we change the base to 2, each beaker can only hold 1 unit of water, or we could say it has 2 states, empty or filled. Base 2, or binary, is very prevalent in computing. This is because it is possible to physically represent and measure a binary state more easily in electronics. For example, a voltage being high or low, a switch being open or closed, or a magnet being north or south. Instead of empty glasses or filled glasses, you can see how the LED off and on states are counting in base 2. In C++, I found that functions cannot return arrays. I had to create a binary array class, which contains a Boolean array as a private member variable. This array can be accessed with setters and getters. I also made a function to set the array from an integer. This way, I could call the method in a single line in the main file. It makes the main file a lot easier to read and adheres to the rule of abstraction, which is one of the pillars of object-oriented programming. I also incorporated a 7-segment display, which has 7 shaped LEDs that are controlled independently. One concern when circuits get more complicated is having enough microcontroller outputs to control all the components. There are 13 outputs on the Arduino, not enough for 2 of these displays. One solution is to use a shift register. Here I'm using the 74HC595N, which can turn 3 Arduino outputs into 8 outputs. It does this by using serial to parallel conversion. Imagine a shift register being a set of 8 switches, on or off. Components can be connected to those switches, in the case of this project, LEDs, which are grounded. There is a control voltage which is passed to each component, but only if its switch is on. The 3 input pins are the data pin, shift pin, and storage pin. The first input, the data pin, will dictate whether the switch is on or off. We do this by setting it to high or low voltage, 5 volts or no volts in this case, using the Arduino. The second input, the shift pin, will trigger when it detects the rising edge of a pulse. That is a low voltage followed by a high voltage. It will shift the value of each switch or slot along by 1. The value in the last slot is discarded, and the first slot, now empty, is filled by whatever the data pin is set to. We can keep repeating this process by setting the data pin and sending a pulse to the shift pin. There is also something called a storage register. The components can't see the switch values we just set until they are copied to the storage register. We do this by sending a pulse to the storage pin, then the LEDs will light up accordingly. This is so we can mess around, shifting the switch values until we are ready to expose the components to the final configuration. While building the circuit, I had to work out which pins of the display corresponded to which LEDs. Then I could work out what data the shift register would need to hold in order to render the correct digits. I made binary arrays which the Arduino turns into high or low voltages to send to the shift register data pin. I used the datasheet for the 74HC595N to see how the pins translated to inputs and outputs. We can connect the output of one shift register to the input of another shift register to get 16 outputs controlled by 3 inputs. If we keep connecting them this way, we could control a large matrix of LEDs with only one serial data output. Again, in C++, I made a shift register object. By abstracting the logic of setting the data write pins, sending shift pulses, and so on, the code in the main file was a lot cleaner and verbose. A switch alternates between a break and a short in a circuit. This is great if we want to control the flow of current, say to control the light. Here, however, I wanted to measure the value of the switch digitally. The Arduino input will take a digital reading for a voltage range. For example, from 0 to 5 volts, the input will return off or low for 0 to 1 volts, and it will return on or high for 4 to 5 volts to allow for physical tolerances. If an unterminated wire is connected to the input, it will read neither high or low and just fluctuate, and this is no good. The way around this is to have the input connected to a ground through a resistor. This way it will always read 0 volts or off. When the switch is closed, a short to 5 volts is made but without a resistor. As the current flow will take the easiest path, the input will receive 5 volts or on. This is known as a pull-down resistor. In the C++ code, I only wanted to read one button event per press. This means I had to catch the point where the previous state of the button was up, but the current state was down. I kept track of these two states, so if the button is held down, it only registers one press. Thanks for checking out my project. I made a lot of mistakes and blew up a few LEDs, but I learned a ton by trying this. I'm eager to find new ways of combining programming with physical electronic devices. If you want to chat about anything in this video, get in touch on social media. Thanks for watching and take care.